In our project, we tried to solve the problem of music transcription. Given an audio recording of a piano performance, we want a model that can recreate the sheet music that this recording was based off of. On the surface, music transcription sounds simple. After all we have to do is track the frequencies at a certain time and correspond each frequency with a given note. However, things aren't so simple. For example, there will be a lot of noise associated with the data that we collect, so the model will need to distinguish what is relevant and what is not relevant. Secondly, when we play a note on the piano, we don't hear a single frequency, but instead several frequencies. These are known as overtones. And when these frequency bands get very close together, it can be very hard to distinguish them. And finally, we will also need to take into account the dynamics of everything. So why do we actually care about this? First, as we just said, piano transcription is very hard. And it's going to be very helpful for amateurs to be able to play songs that they've heard before, but don't have the skill or resources to get a transcription of the songs. But more importantly, it has very close ties with natural language processing. Not only are we converting from one sequence to another sequence, but only a certain sequence of musical notes sound nice together. Just like how a certain string of letters and characters and words sound nice within language. As a result, this program will also need to learn music theory as well.
We use Maestro Dataset for this project, arguably the largest dataset for our task. This dataset consists of pairs of WAV files and Midi files of piano audio, and in total they amount to 200 hours. WAV files are raw audio files, and the corresponding Midi file contains labeled information of each note, such as when, what, and how strong it was played. In our project, Midi files are the ground truth, and our model takes WAV files as an input and trains against Midi files. However, both file types are hard for the model to understand, so we needed to do some pre-processing. For data processing, we had to do two major tasks. One is converting WAV files to a spectrogram. The other task is converting Midi files to a certain kind of form, which is easier for the model to train. We choose to convert Midi files into arrays with time on the x-axis and note on the y-axis. As Midi files hold when each note begins, how long it lasts, and how strong it was played, we divided Midi files into three arrays respectively. First array is the onset array, the second array is frames array, and the third array is velocity arrays. Since every song has a different length, we divided all the spectrograms and labels into 20-second segments. So our model will take a 20-second long spectrogram as an input. The downside of this approach is that we might have a clip at the end of the song that is shorter than 20 seconds. This can be resolved by zero padding. However, since most songs were several minutes long, we didn't think this would make a noticeable difference and opted to simply ignore the last few seconds. Using onsets, frames, and velocities as labels, we were able to create a model that made three predictions.
Now, about the model. To get predictions, we first feed the spectrogram into a stack of convolutional layers, and the output is fed into a transformer encoder, with a fully connected layer possibly in between. We did this for both the onset, frames, and velocity predictions. However, to predict frames, the onset prediction was also fed into a transformer encoder. For all the models, we use cross-entropy loss as our loss function, and then our optimizer as our optimization function. Except for the velocity model that we use mean square error. Let's go over some of the reasoning behind this. First, why CNN? We chose CNN because image and audio both have two-dimensional time frequency input representation. The fact that CNN performed well in image classification problems also suggests that it could be used for music transcription. Now, why the transformer encoder? As you can see from the diagram, the original paper on which our model is based used LSTM as a decoder. We decided to replace LSTM with a transformer encoder. Because ever since its introduction in 2017, the transformer has consistently outperformed recurrent neural networks in many sequence modeling tasks. That is why we believe that by using transformer in our model instead of using LSTM, our model will perform better than the original paper.
I'm also a pianist, and I'm at the piano store. This is the first time I've played the piano since coming to Toronto, hence I've made several mistakes. However, the model still performed better than we expected. important to know that the data used for music transcription is inherently biased. A piano has 88 keys, but a human only has 10 fingers. Therefore, the accuracy is not a very useful metric, because even a model that predicts no notes can achieve a very high accuracy score. Therefore, we decided to use precision recall and F1 score to evaluate the performance of our model. We are able to achieve an F1 score of 78.85%, which slightly outperforms Google's 2017 model, which our model is based on. However, just 2 weeks ago, Google released a new model that is also based on Transformer. They were able to achieve a F1 score of over 82%, which is much higher than our model. However, they use a completely different architecture, which is based on the cutting-edge research of generalizing transformers to other tasks. At first glance, the frames model seems very accurate. However, many of the notes can be broken into smaller segments. We think this is due to our loss function, which is a pixel-wise cross-entropy loss, since only mispredicting 1 pixel can break a note into 2, but will only incur a very small loss. Discounting the very low notes, the ONSES model makes very accurate predictions. Hence, using these predictions to inform a classical algorithm may improve the overall transcription performance our model can achieve. Overall, we still completed our goal to demonstrate that transformers are substantially better than LSTM, to the point where we were able to perform better than Google's 2017 model with far less resources.